Before we dive into today's episode, make sure to hit that subscribe button. It's the best way to stay updated with our latest insights.
Ladies and gentlemen, welcome to the CTSS Academy podcast. The energy is electric. The crowd is alive. Let's dive into greatness. We're champions strong.
Before we start the show, don't forget to check our new ebook, Kill All Bugs, Learn Software Testing in One Day. For a limited time, it's only $9.99. Links in description.
All right, welcome back to the deep dive. So if you've ever thought about a career building, the digital world all around us, you've probably hit this wall.
Oh, yeah.
This wall of confusion. Computer science versus software engineering.
It's a huge one. The degree titles, they sound almost the same. The job descriptions seem to overlap everywhere.
And everyone just uses the terms interchangeably. It's a complete maze.
It is, and we know you're looking for some clarity, so we've gone through a whole stack of source materials, the core definitions, curriculum differences, salary stats, and maybe most importantly, the high-stakes professional challenges.
Just to give you a map.
Exactly, a definitive map.
Because our mission today isn't just, to define the terms. It's to really distill the essential differences so you can figure out which path is right for you. Is it the theoretical puzzle or the practical build?
And to start, we really have to get this one thing straight. Even though software engineering, or SE, grew out of computer science, or CS, they are fundamentally different approaches now. CS is, at its heart, an academic discipline. It's asking these deep, abstract and mathematical questions about the limits of computation. It is the science part.
And SE is the application of that science. It's looking at the how.
Right, the process. How do you turn those mathematical possibilities into reliable, huge systems that actually work in the real world?
It's like the difference between physics and structural engineering.
That's the perfect analogy. One discovers the laws of the universe, the other builds the bridge that won't collapse.
Okay, so let's unpack that. Let's start with the definitions that our sources give us. Computer science.
Right. So CS is defined as the discipline that involves the design and the understanding of computers and computational processes.
And it's huge, right? It covers everything. Algorithms, network security, AI.
It's a vast scientific topic. The sources say it's about how computers perform theoretical and mathematical jobs. It's designing algorithms, designing theories to manipulate data.
So think less about building the latest app.
And more like discovering the laws of gravity for digital systems. It's very scientific, very abstract.
Okay, now contrast that with software engineering. SE is defined as a highly disciplined process.
Yes, process is the key word. It starts by looking at what the user needs, then it moves into designing, building, and rigorously testing software to meet those specific needs.
So it's the study of how software is actually built for commercial use.
Exactly. For use in the real world, which means you need control, predictability, teamwork. It's about building that certified jet engine after CS has discovered the theory of flight.
That distinction really helps. But okay, let's get practical for a minute. For you listening, trying to choose a path, how does this split guide you?
Well, it really boils down to specialization versus the whole life cycle.
What do you mean?
If you're passionate about the really specialized frontier fields, I'm talking about pushing the boundaries of AI or machine learning, security, cryptography, advanced graphics, then you need that deep mathematical foundation from computer science.
Because CS gives you that fundamental knowledge of how the computer actually works at its core.
Precisely.
Okay, so what if I'm less interested in, say, inventing a new AI algorithm and more concerned with managing a huge team to deliver a new software system on time and, under budget?
Then software engineering is your direct path. SE is what trains you in the overall life cycle. How is this specific thing built? How is it maintained? How is it tested? It's all about the repeatable methodology that prevents total chaos.
And what's interesting and also a little confusing is that the sources say software engineering is technically a field of computer science.
Right. They're not totally separate planets.
More like adjacent continents.
A good way to put it, CS is the vast foundation for everything. But the scope of SE is really tied to the immediate future of technology. How do we deliver complex products now and in the next few years?
Whereas CS is thinking about bigger, longer-term problems.
Exactly, like the fundamental structures of cloud computing or the underlying mechanics of AI technology, things that will pay off down the line.
So if CS is about the why and SE is the how, then we should see that in what they teach. Let's dig into the coursework, because I think that's where the philosophy really shows itself.
It absolutely does. Look, in software engineering, you're not just learning to code, you are learning system discipline.
Right.
You're highly likely to take dedicated, required courses on project management, scope, budget, team coordination, both in undergrad and grad school.
And that makes perfect sense. Because an SE failure is often a process failure.
It's a process failure. If you're responsible for a massive team and delivering a product to a client, project management is not a soft skill. It's a hard requirement.
It's the requirement.
Exactly. Now, in computer science, the focus shifts. You're studying how data is stored, how it's processed, how it's applied. You're diving deep into theory.
But they must learn some project management now.
They do, but the sources are specific here. It's often included, but usually as part of a general software engineering course within the CS program. It's seen as complementary knowledge, not the core discipline.
Got it. Okay, let's zoom out a bit. Why are both of these so critical right now? What's the unique value that each one brings?
Well, the need for software engineering is really rooted in managing complexity and commercial reality. Good SE practices let you improve quality, increase productivity, reduce development costs.
And actually deliver what the customer asks for.
Most importantly, yes. It's about creating predictability in what can be a really chaotic environment.
And the need for computer science.
That's about foundational innovation. CS is where the next generation of computing capabilities come from. It's the engine that helps us study the fundamentals mathematically and logically, so engineers have something new to build with later.
Okay, let's get to the question everyone is waiting for.
Ah, yes, the money.
The money. If you commit to either of these paths, what does the financial picture look like? Give us the bottom line from the U.S. salary data.
All right, so our sources show that the average salary for a computer scientist in the U.S. is $103,643 per year.
103,643. And what about the professional who's focused on the building, the delivery life cycle?
The average salary for a software engineer, it comes in slightly higher, actually, $107,932 per year.
That is interesting. It's a slight edge, but it's measurable. Why do you think that difference is there, especially when CS is arguably more specialized in these, high theory fields?
Well, if you look at the market, I think that small difference probably reflects the immediate high-value demand for reliable delivery.
Right.
Companies desperately need experts who can not just write complex code, but who can make sure millions of lines of that code are delivered on time, are tested, are maintained. That structured process of SE, it carries a very high market value because it reduces risk.
That makes a lot of sense. That financial edge reflects the pressure, which is a perfect lead-in to the next part, the critical challenges. Because when things go wrong in these fields...
Oh, they look completely different depending on your focus.
Tell us about software engineering first. The risks there seem very tied to the real world.
They are, because SE is about delivery. The challenges are all about the catastrophic cost of a failure in implementation.
And we're not talking about abstract costs. The sources are very specific here. They list safety-critical areas like space systems, aviation, nuclear power plants.
Places where a software bug, a faulty construction, means lives are at risk.
Lives are explicitly at risk. An engineering process failure there is. It's unforgivable.
Absolutely. And beyond just safety, SE pros are always fighting against huge market pressure. They need fast turnaround times, and they have to solve this incredibly complex puzzle of getting different software systems to talk to each other.
Which is basically the core struggle of any big company today.
It is.
Okay, so let's switch gears to the challenges for computer science. Their concerns feel bigger, more about infrastructure and security.
They are. They're tied to the very underpinnings of our future technology. For instance, the sources point out that the Internet's basic infrastructure needs a fundamental redesign to handle what they call the new Internet.
Okay, we have to unpack that. What on earth is the new Internet?
So what the sources mean by that is an Internet defined by, well, a few things. The massive integration of the Internet of Things, or IoT, heavy reliance on global cloud services, and just explosive mobile connectivity.
So it's not just a faster internet, it's a An exponentially more complex and interconnected one.
Exactly. And that leads to this mind-blowing statistic in the material.
The one about 2020.
Yeah. A projection that by 2020 there would be 100 billion objects connected to the internet.
100 billion. That's an insane number. Everything from your doorbell to industrial robots.
And that explosion is the core challenge for CS professionals. It puts enormous stress on the infrastructure and, of course, creates massive security vulnerabilities.
Which brings us to their highest concern.
Right. According to the sources, the number one thing CS professionals rated as their highest concern was data leaks and the exposure of sensitive information.
So you have life and death consequences for the engineers,
Right.
and these huge theoretical security crises for the scientists. That must lead to very different professional standards.
It does. The best practices really show a clear contrast in focus. It's ethics versus methodology.
Explain that. What does it look like for the software engineer?
For the engineer, the standards are very heavily centered on ethical responsibility and professional quality. You have to act beneficially for both your client and your employer. You have to meet the absolute highest professional standards.
Maintain integrity, independence.
All of it. You are mandated to promote an ethical approach through every single phase of development and maintenance. The goal is trust and reliability.
That focus on ethics seems tied directly to those safety-critical systems you mentioned. The engineer is signing off on something that just cannot fail.
Precisely. Now, for the computer scientist, the best practices are less about corporate ethics and more about methodological efficiency.
How so?
They focus on things like collaboration, making incremental changes to algorithms, and this one crucial piece of advice: optimize your software only after it works correctly.
Ah, right. Don't try to be clever until you've actually proven it works.
It's the scientific mindset, right? Prove functionality first, then refine it.
And that difference even shows up in how they document their work.
It does. The CS standard is to document the design and the purpose, but not the mechanics of the code itself.
Why not?
The focus is on the high-level understanding, the what's and why. The low-level how is left to be self-evident from the code, or changed later. It shows that the CS product is really the idea, the theory. The SE product is the working, maintainable thing.
So when you boil it all down, what does this all mean for you, the person listening and trying to decide? We started with all this confusion.
And hopefully we've brought some clarity. Look, both of these paths, CS and SE, they're fantastic. They offer immense professional fulfillment, great financial rewards. They're both the best in their own distinct ways.
The final choice, then, really just hinges on where your passion is.
That's it. If you are driven by deep specialization, by the mathematical puzzles, by inventing the next generation of what's possible in AI, security, databases, then computer science gives you that theoretical foundation.
But if you're motivated by the process of creation itself, the challenge of managing complexity, of ensuring reliability, of seeing a huge product get built, tested, and maintained,
then software engineering is your direct route to that high-stakes delivery.
So the world needs both, the abstract thinker and the discipline builder.
It desperately needs both. But let me leave you with one final thought, something to chew on that connects these high-stakes challenges we just talked about.
Okay, this is where it gets really interesting.
We talked about the high-stakes failures in SE, like in aviation, and we said the highest concern for CS was data leaks. So if we tie those together with that projection, the 100 billion connected objects on the new internet.
Right.
When a critical connected system, let's say an air traffic control system, when that system fails, not because of a bug in its construction, but because of a security breach that exploits a deep theoretical vulnerability, whose fault is it? Which discipline, the theoretical security specialist or the lifecycle engineer, bears the greater professional and ethical responsibility?
Wow. That's a question that really gets to the heart of our connected future, doesn't it? It means the scientist and the engineer have to be in perfect lockstep to keep everything running. Thank you for joining us on this deep dive. We hope this has clarified your path forward.
Thanks for listening. If you found value in today's episode, please subscribe and leave us a review. It helps more people find the show. See you in the next one.
Hey, yo, haven't you checked out our new book yet? Link in description.